In the first problem we want to work through today, we're going to have a thin sheet of metal, say, shaped like a triangle. The base of the triangle is going to be 2 centimeters, and the height of the triangle is going to be 1 centimeter. If you've got an isosceles triangle, it's also going to be an isosceles triangle like this. It probably is most convenient to choose your coordinate system, to have the midpoint of the base be at the origin, the base be along the x-axis, and the height be along the y-axis. So there's our x-axis, there's our y-axis. I made the base of the triangle be 2 centimeters, so this would be -1 and this would be +1. Both x and y are in centimeters. And I said the height was 1 centimeter, so this would be y = 1 right there. For the sake of just practicing problems where maybe it's not clear what to do, we do make kind of strange assumptions. And the assumption in this case is that the thin plate does not have a constant density, but a density that depends on x. The density is a function of x here. Now, there's nothing explicit in the reading in this section that addresses exactly this kind of question, where we're going to try to figure out the mass of this, and I'm going to do a little bit more. We're also going to figure out the x coordinate of the center of mass. Nothing explicitly in the reading that gives you an example just like this, but using principles like what I'm going to show you here as we solve this, you should work at developing flexibility to solve new kinds of problems. And yes, I will assign problems that are somewhat similar to this, but with some twists. Maybe the density will depend on y instead of x. Actually, on Friday, we'll do a multivariable example where the density depends on both x and y, and we'll have to do a double integral instead of a single integral. Doesn't that sound like fun? That'll be a little introduction to multivariable calculus. Our density here is 1+x. That's the formula here. What would the units be? This is not a thin rod, so it's not a linear density, say in grams per centimeter. It's a thin plate, a thin sheet, a lamina. Mass per unit area? Yeah, say grams per square centimeter instead of grams per centimeter. We're pretending it's so thin, we ignore whatever tiny thickness it has and think of it as a two-dimensional object. That's what people do when they do mathematical modeling, is they try to make things as simple as possible. As usual, you want to slice. Break this up into pieces. How? Since the density depends on x, you'd want to slice it in such a way that along thin slices, the density is approximately constant. Constant value of x. So you want to use vertical slices, not horizontal slices, right? Because along horizontal slices, x would vary quite a bit. The density would not be constant. Along a vertical thin slice, the density would be approximately constant. Pretend x is, say, right here, and I'm thinking about a thin slice there of width delta x, small width delta x. It doesn't matter exactly where I label the x here. It could be the left endpoint, it could be the right endpoint, it could be the midpoint. It doesn't matter, because remember, in the end, we're just trying to think about it to set up an integral. And when you do the integral, you don't have to think really about where x is in this picture. Right? And I'm using x both as a label for the axis, as a variable, and as a particular point. I drew it over here, but I could have drawn it over there. What am I after again? I'm after the total mass of the triangle. I'm also going to try to figure out the x coordinate of the center of mass, x bar. The density is not constant. It varies. Its formula is 1+x. Think about this. If you're close to the leftmost point over here, x is close to -1, the output of this function would be close to 0. It's very tissue paper-like over here, you might say, not very dense. On the other hand, as x gets close to +1, the output gets close to 1 + 1 is 2. It's a lot more dense over there. The molecules, I don't know, are either they're more tightly packed or they're more massive molecules or something, I don't know. I don't know how you actually manufacture something like this, but we don't have to worry about that. This is all pretend for the sake of illustrating ideas, okay? Don't worry about practicalities like that. You have a lot more flexibility in math. Did you know you can go faster than the speed of light, by the way? Did you know that? Not in real life, but in your mind. You can imagine going faster than the speed of light. There, I went from here to Andromeda in 1 second. In my imagination. That's not real, is it? It's real in my mind. I just imagined it. Okay, math is infinitely more flexible than real life. So we can do things like this. Anyway, what's the approximate mass of the thin slice? Maybe we should call it, how about delta M? Use a little m here because later we're going to use a capital M for a moment when we try to figure out the center of mass. There's the small mass of thin slice. The density is approximately constant. Take that density and multiply times the area of the thin slice. This would be approximately delta of x times delta A. This is the small mass of thin slice. This is the small area of thin slice. So do I integrate delta of x dA? Well, that doesn't sound so easy to do. I want to get this in terms of delta x. Okay, now we were used to this. Pretend that's a rectangle. Okay, it's really a trapezoid, but pretend it's a rectangle. Do another approximation. Approximate delta A with the height of the rectangle times delta x. What's the height? I guess I need the blue graph, don't I? What's this function of x here, this upside down v? If you think about it, think about the absolute value function. Its graph looks like an ordinary v, bottom at the origin. If you reflected that across the horizontal axis and got an upside down v with the top at the origin, you could then shift it up by 1 unit to get this graph. So negative absolute value of x plus 1 would be this graph, or if you prefer, 1 minus the absolute value of x. You could think of that as a piecewise function if you like. Absolute value of x equals x when x is positive. So this is 1 minus x if x is between 0 and 1. You also see this part of the graph has a y-intercept of 1 and a slope of -1. On the other hand, if x is negative, the absolute value of x is the opposite of x. So you get a minus x, you get a 1 plus x if x is between -1 and 0. Doesn't matter whether you include 0 in the first formula or the second, because they have the same value at x equals 0. So that is the height. I could have called it h of x instead of f of x, but I called it f of x. Height times width gives you the delta A. Delta x is the small width of the thin slice. Okay, I might as well continue labeling this. Small width of thin slice. From this, we can then figure out the total mass as a sum of the little masses, which is then approximated as a sum of things like this. And then you jump for joy because you look at that and you say, hey, that looks like a Riemann sum for this function. I just now need to let delta x go to 0. And the summation magically morphs into an integral. Okay, again, it's not magic, but it's fun to pretend. I integrate delta of x times f of x. I need a definite integral to get an answer, so I need limits of integration on x You look at the picture, you say, oh yeah, x goes from -1 to +1. Let's go ahead and do this by hand. Then we'll check it with Mathematica. But then for the rest of the integrals that we do today, we'll just use Mathematica, even though they could be done by hand. Just for the sake of saving time on the homework, you will want to use do it by hand. To do this by hand, though, we do need to use a property of integrals because of the piecewise formula for f. I need to use this formula for f when x is negative and this formula when x is positive. So I need to break up the integral into the sum of two integrals, one from -1 to 0 and one from 0 to 1. In both integrals, delta of x has the same formula, 1+x. When x is negative, f of x also has the same formula, 1+x. So I get 1+x squared. When we go from 0 to 1, delta of x is 1+x, but f of x is 1 - x. All right, do this by hand. We need to expand those binomials. When I square 1+x, I get 1 + 2x + x squared. When I multiply 1 + x times 1 - x, I get 1 - x squared. Outside and inside terms cancel. Do these integrals, be careful. The main thing is just not to make a mistake here. Maybe you want to use parentheses around things just for extra emphasis to keep yourself from making a mistake. Hopefully I don't make a mistake. When we plug in 1 up here, oops, I made a mistake. -1 to 0, sorry. When we plug in 0, we get 0. When we plug in -1, use parentheses, we get to subtract what we get when we plug in -1. I get -1 + 1 - 1/3. Right, -1 there. -1 squared is +1. -1 cubed is -1 times 1/3 is -1/3. The second one, I plug in 1, I get 1 - 1/3. I plug in 0, I get 0. The -1s cancel, the -1 and +1 cancel. This all becomes +1/3 and then +2/3, giving me 1 for the final answer. It is a mass. This would be in grams. 1 gram. Okay, use singular. Pretty simple answer. Is there a way I could have guessed the answer without doing all this work? I think this one's simple enough that we could have. If the density had been constant, in particular if it had been 1 gram per square centimeter, I wouldn't have to do an integral to figure out the mass. I could just multiply that density by the area. It's a triangle with a base of 2 and a height of 1. 1/2 base times height would be 1. 1 times 1 would be 1. 1 gram. 1+x has an average value in the x direction of 1 as x goes from -1 to 2. It varies from a value of 0 to 2. Having a value of 1 when x is 0, when you're along the y-axis there. The average density for this symmetric object seems to be 1 gram per square centimeter. That would cause me to predict the answer to be 1 times 1, 1 gram ahead of time, and this confirms it. Let's check the calculation with Mathematica as well. But when we check it with Mathematica, let's do it, do the integral from -1 to 1 using the absolute value formula for f. So the delta of x formula is 1+x. The f of x formula is 1 minus the absolute value of x. Instead of breaking it up into two integrals, Mathematica should be able to handle it as one integral like this, and yes, get an answer of 1. What's the center of mass of this triangle in just say the x direction? Since the density depends on x, it's probably going to be a better idea to just focus on finding x bar instead of y bar. In fact, if we tried to find y bar, we'd have to do a double integral. So again, maybe that'll be for Friday. Let's find the moment with respect to x equals 0 first. And then we need to divide by the mass, which will be easy because we'll be dividing by 1. What's the small moment delta capital M of that thin slice? Well, what is the moment in general? For a point particle along an axis, the moment with respect to the origin is the mass times the position, m times x. Little m times x. The moment of this thin slice in the x direction would be its position times its mass. Position with respect to x equals 0. X. I drew it positive, but I could have drawn it negative. This is x times the mass, which is labeled delta little m. It's a small mass because it's so thin. Call it delta little m. And from before, that little mass, delta times little m, this was delta of x times delta A, the density times the area. And that was approximately delta of x times f of x times delta x. So this is approximated by x times delta of x times f of x times delta x. Sorry again that we're using deltas in two ways in these things. The total moment with respect to x equals 0 then would be the sum of these little moments. It would be approximately a sum of things like this: x delta of x, f of x, delta x. And this now is a Riemann sum for that function. We let delta x go to 0. Total moment is the integral of x times delta of x times f of x dx over the interval of integration, which was -1 to 1 for the triangle. Now think about this. This triangle is denser on the right than it is on the left. It's like tissue paper on the left and maybe semi-dense metal on the right. We should expect an x-coordinate of the center of mass that's positive. Should be to the right of x equals 0. X bar should be positive. So therefore, this integral should be positive. Let's see if it is. Just copy and paste this integral. Put an extra x in there. Should get a positive answer. I need to re-enter this stuff. Re-enter the function. Positive 1/6. That's the moment of the thin slice, excuse me, of the entire mass in the x direction. Therefore, x bar itself is the moment, capital M, divided by the mass, little m. 1/6 divided by 1. Units would be, for the moment, grams times centimeters. Units for the mass would be grams. The grams cancel, giving you 1/6 centimeter for the location of the center of mass in the x direction. Okay. Did it on Mathematica as one integral from -1 to 1. If you had to do it by hand, since f of x was 1 minus the absolute value of x, you'd want to split it up into two integrals and add the results. One from -1 to 0, one from 0 to 1. Add the results.